Hello. Today we're going to consider a slightly different form of the derivative called a differential form, or just differentials. And so let's suppose f of x is differentiable at x equal a. And so, kind of rough idea here, I've got some value x equal a. So therefore, this is the point a comma f of a. And we know from before that the slope of the tangent line to the curve at x equal a is the derivative at a. This slope is f prime at a. Okay. And I know the equation of the tangent line would be y minus f of a is equal to f prime at a times the quantity x minus a. We've seen that already a bunch. So let's, instead of dealing with, now this is all set up in terms of an x and xy axis, the normal axis. Let's suppose that we consider a shift in our axis, and let's make the axis go through the point a comma f of a. And so instead of calling this the xy axis, because that's the original axis, axes, I'm going to call this the dx dy axis. Okay? Now, my tangent line to the curve goes through the origin of this axis. So the tangent line, the equation of the tangent line with regards to the new axis would be y is equal to dy is equal to f prime at a times dx. All right, my y value in this new axis is 0. My functional value in the new axis is 0. Right. This goes to the point 0, 0. And so it's dy minus 0 is equal to f prime at a dx minus 0, or just dy is equal to f prime of a dx. And we can kind of consider this in general. It doesn't have to be, for a specific x equals a. We can generalize this for any place where the derivative exists. If f prime of x exists, at some specific x, then doing the same process, we get dy is equal to f prime of x dx. And again, basically all I'm doing is, one way of looking at this is creating a new axis, a new set of axes, the dx axis and the dy axis. Okay? And again, my tangent line goes through the origin of that axis. Now, if you notice, this is, remember, our basic derivative, f prime of x, had the form dy dx. And so, we've always thought about dy dx as a single entity. But if we think about this now in a different way, according to like this new axis, then we can, in effect, think of this as a quotient, and therefore we get dy is f prime of x dx, the same thing I have up above. And so this is called the differential form of the derivative. Basically, I'm thinking of dy and dx as, small values, very, very small values, and we're looking at this infinitesimal values, but we're looking at this basically as a quotient in that way. So, given a derivative, I can, use this kind of, breaking this apart to write the derivative in differential form. For example, simple example here, if I have y is the square root of 2x plus 6 over x, or, this would be x plus 6 to the 1/2 power over x. The derivative in this case would be bottom times the derivative of the top, which is 1/2, x plus 6 to the negative 1/2 times 1. It's a chain rule. Minus the top times the derivative of the bottom, which is 1, all over the bottom squared. Or this gives me the square root of, let me write this a little bit more space, the square root of, this gives me x over 2 square roots of x plus 6 minus the square root of x plus 6 all divided by x squared. And let me go over here, and I guess I'll erase my picture. Limited board space can be a real pain. But getting a common denominator, multiplying this into so I get a single fraction. If I multiply, both numerator and denominator by 2 times that square root, I get x minus 2 times the quantity x plus 6. How did that become x plus 6? This should be 2x plus 6. Well, that's unfortunate. Let me just change the problem. It'll be easier than trying to make it. There we go. That's much easier. I get x minus the quantity 2 times x plus 6 all over 2x squared times the square root of x plus 6. Right. If I take this and multiply the big fraction by 2 square roots of x plus 6 over 2 square roots of x plus 6 and distribute, the algebra works out accordingly. And so this then becomes negative x minus 12 over 2x squared square root of x plus 6. Now this is my derivative, or again in the other notation, dy dx. And so therefore the differential, or the differential form would be dy is equal to this function all times dx. And we can basically look at this as what happens to my dy value when I put in a small dx value. Again, going back to my picture that I erased, we had this new axis, and the question is, what's going to happen to my dy value when I make a small change in dx, whatever that is, around that point, whatever my point is. And so let's find the value of the differential when x is equal to let's see, what do I want? How about when x equals 3? Make it kind of simple. And dx is equal to 0.01. And so basically we just put in those values in. And so in this particular case, we would then get the value of the differential at those particular values. dy would equal -15 over 2 times 9 times the square root of 9, which is 3, all times 0.01. And we can kind of simplify this down a little bit. This is, -5 over 18 times 0.01, and whatever that comes out to be. I don't want to figure that out, but basically what this says is that when I change my x value by 0.01 from this point where I'm creating my new axis, that my dy value is going to change by whatever this number is. So, okay, this form, the differential form, actually comes up a lot later. I will hopefully remember to mention it at the time. But when we talk about antiderivatives or integrals, we have functions that are in the differential form. So it actually does come up later.